All right, so we're going to talk a little bit more about cardiovascular adaptations. The objectives or the outcomes are the same for this one as the last one. I'm going to start off with the same first slide, but now we're going to look at cardiac output, blood flow, and blood volume. Okay, so look at this figure here. On the x-axis, we've got intensity as measured by treadmill speed. On the y-axis, we have cardiac output. Now, if you notice that essentially cardiac output is the same for a given intensity, but notice that we hit a plateau, a much higher plateau after training. So max cardiac output in the blue is about 20 liters a minute, and in this case, after training, it's about 28 liters a minute. So that's like a 40% increase. All right. So training doesn't do anything at submax intensities because yes, you have reduced heart rate, but it's compensated for by that increased stroke volume. And remember, ultimately, we're trying to maintain cardiac output to deliver a given amount of oxygen. And so we might be doing it more efficiently, but it's not going to change cardiac output. However, maximum cardiac output increases, and then the benefit of that is that we can go at a higher intensity for a longer period of time. And this is arguably the most significant, most important adaptation that occurs after aerobic training because you're able to deliver more oxygen. And that's really the limitation for most of us when it comes to VO2 max, being able to deliver, not being able to get, it's not getting oxygen in, and it's not the muscle being able to use the oxygen, it's actually being able to deliver enough oxygen. Okay, and so there are some adaptations that occur with blood flow. So as we've talked about, when we exercise, we're going to deliver more blood flow to the muscle. We want to make this efficient, right? Everything's about being efficient, trying to maintain homeostasis. And so there are 4 things that we can do to improve blood flow efficiency. So we can have more capillaries, we can recruit more capillaries, we can do a better job of redistributing the blood, and we can have an increased blood volume. Okay, so with capillaries, endurance training increases the capillary density, and so that makes it a lot easier to get oxygen into the muscle cell. If there's more places where a muscle cell can pull oxygen, that's going to be very beneficial. We can also recruit more capillaries. We kind of talked about this with VQ matching, about how not all capillaries are recruited at all times for a variety of reasons. Well, the same is true in a muscle cell. And so if we can recruit all of the available capillaries, it's going to make it easier to get oxygen in. Ultimately, we're trying to deliver that oxygen to the muscle. So with blood flow redistribution, we want to do everything that we can to get that blood flow, as much blood flow to the active muscle as possible. Okay, notice kind of what changes here. So we've exploded this view out. So you've got blood flow going to the muscle. This is muscle here. Notice that as we increase exercise intensity, how much blood is going to the muscle, right? So by this point at rest, it says blood flow 3 liters a minute. So 22 out of the 25 liters of blood is going to your muscle. So that's what, almost 90%. Whereas at rest, it's not quite like that. You've actually got about 10% going, if that. And so there's some evidence to suggest that we actually might be able to distribute this blood to the muscle cells that are going to use the oxygen. Okay, and so we're not going to spend as much blood or deliver as much blood to those glycolytic fibers that don't need the oxygen. Next, we have blood volume. And so when we train, we have an increased blood volume, and this happens 2 ways. One, will increase the amount of plasma, so the amount of fluid, as well as the number of red blood cells. And so ultimately what happens is, if we've got more red blood cells, more blood volume, we can carry more oxygen. Okay? And so just to give you an idea, if we are able to increase the concentration of hemoglobin by 1 gram of deciliter of blood, that's ultimately going to improve our oxygen carrying capacity by 5 to 7%. That'd be pretty significant, right? So if it doesn't work exactly like this, but we've talked in class about Morgan running the mile or the 5K or whatever. So I don't know off the top of my head what her time is, but let's just say it's 17 minutes for a 5K. Okay, if I told her, hey, that just with training, just improving blood volume, you could take nearly a minute off. So 5% of 17 is 0.85 minutes, okay, which is 51 seconds. She'd take it in a heartbeat, and she'd be well on her way to go running at nationals, dropping a minute off just with blood volume. So this is accomplished, like I said, with plasma volume, and this occurs because we'll produce more plasma proteins. The job of plasma proteins such as albumin is to make sure that we keep the fluid in the blood. Okay. We also will release ADH, which allows us to reabsorb any fluid or more fluid that goes to the kidneys. And as a result, if I've got higher plasma volume, I'm going to have a greater stroke volume. We're also going to change this with red blood cell mass. Okay. And we can see that from this figure here. Okay. So notice that in this person, just in this little figure that's from the book, they've got a total of 5 liters of blood. 44% of that is red blood cells. So if you did the math, 2.8 liters is plasma, 2.2 liters. That kind of sounds weird, right? That you've got 2 liters of red blood cells in your body. Okay. Well, we've increased plasma volume from 2.8 to 3.3. And we've increased the number of red blood cells from 2.2 to 2.4. That's about a 10% increase. Now notice that because plasma volume increases a little bit more, our hematocrit actually drops. But we've got more red blood cells. If we've got more red blood cells, we can hold on to more oxygen. But there's a benefit to having a lower hematocrit in that the blood won't be quite as viscous, which means it'll be have an easier time to flow. So the heart doesn't have to work as hard, and now we're delivering oxygen more efficiently. So can we just improve VO2 max for forever? And the answer is obviously no. Generally, trained individuals are somewhere around 50. I'm hoping I'm still there. I think that I am. Elite athletes can have 80. I think the highest that they've ever recorded is high 90s or mid 90s by a Norwegian cross-country skier, but there are some allegations that he was blood doping at the time, so it's not necessarily real. But go from trained to elite, that's a 60% difference. Okay, that is a massive amount. And so to get from 50 to 80 would take a lot of time, a lot of training, and a lot of good genetics. But that's kind of how it is with anything, right? If in these individuals that have a really high VO2 max, they've got a high maximum cardiac output, and then they've got just a high oxygen carrying capacity within their bloodstream. But they also have to have these adaptations that we're going to talk about later in the week with their muscles and with their lungs and stuff like that will help maximize oxygen intake, delivery, and uptake. So this should say lecture 1013. So we're going to, okay, 3 changes, the benefit of those changes.